In this lesson, we'll talk about integration by substitution. Integration by substitution is the reverse of the chain rule. So what we need to do is consider what the chain rule used to do and think about how could we actually reverse this process. So let's take a look at what this looks like. First off, we'll start with the function e to the x squared. And let's just take the derivative of this function just like we did in class. E to the x squared is kind of like the idea of e to the u. And remember, the derivative of e to the u is still e to the u. And don't change the u. Remember, always leave the inside alone. And then we will multiply by the derivative of the inside. So we get e to the x squared times 2x. What this means is if we write the integral of e to the x squared times 2x dx, then we get the original function, e to the x squared plus c. So that's the idea. A problem that could be solved by the chain rule. If we recognize it as a derivative using the chain rule, we can reverse the concept of the chain rule. Let's try another one. The derivative here, the 1/6 can stay in front, and then the 6 comes in front to bring this down to x squared plus 1 to the 5th power. Now that was the derivative of the outside. If we multiply by the derivative of the inside, we'll be doing the derivative of x squared plus 1. You'll notice that the 1/6 and the 6 cancel, and we end up with simply x squared plus 1 to the 5th power times the derivative of x squared plus 1 is 2x. So with that said, if we were to take the integral of x squared plus 1 to the 5th power times 2x dx, we could recognize that this is the derivative of the inside, and we would get what we started with earlier, 1/6 x squared plus 1 to the 6 plus c. And I might point out also, if you think of this as u to the 5th power, u to the 5th would become u to the 6th over 6. And we're getting somewhere with this. Next one. To take the derivative of natural log of something, it's like a natural log of u, and we get 1 over u. Again, leave the inside alone, times the derivative of the inside. So I get 1 over x squared plus 4 times 2x. And from there, we could see this corresponding integral. If we needed to integrate 1 over x squared plus 4 times 2x dx, we could see that if this is thought about as the u, if you will, then your derivative of the inside is right here, and the integral of 1 over u would be the natural log. The absolute value, we'll leave it out simply because it's already positive. But anyway, we get the natural log of x squared plus 4 plus c. So now let's talk about this substitution rule. In this case of everything that we did, we had the derivative of the inside was 2x every single time. So in order to do this reversing of the chain rule, what we need to do is look for something to call the inside function. And what we need to do is look and see if we can find its derivative, and we're going to call these things u for the inside function and du for the derivative of the inside. And then what we do is when we create those two equations, we will use both of them to change the integral to an integral in terms of u. We will solve the integral, and then once we solve the integral, we'll have an answer in terms of u that we need to change back. We call that step back substitution. And one important thing about this rule, you pick u, and then du is calculated. Du is always the derivative of u. So again, you pick the value u, and then take the derivative to calculate du. One of the issues that we run across is sometimes this method just doesn't work. Sometimes step 2, sure, you can get an integral and you can try to do a substitution, but you just can't find one. Another thing that might happen is you might successfully make the substitution, but the new integral cannot be solved. But either way, this method does work pretty well. And everything that we'll do in our class will be doable using this method. And then I'd give you one warning, is that when you're doing your Wiley Plus somewhere, keep in mind that Wiley Plus likes the letter W. Now I don't know why they use W in the book, they just chose it. It's not a standard one, so I decided to stick with what's the standard form. We often call this technique u-Substitution, so I'm not sure why they used the letter W in this particular book. Let's see if we can do some of these. The idea is you want to find something sort of on the inside that you can take and call the inside function, but you want to do so in such a way that the derivative of the inside is present somehow in the function. So if you look at this problem, the x cubed is on the inside of the function. It's the inside of the e to the u. So if I were to let u equal x cubed, what you'll notice is that the derivative is actually in the problem. The derivative of x cubed is 3x squared. And let's write that down. We're going to call this du, and the way that we write this is we take the derivative of x cubed, which is 3x squared, and we append it with a dx. This is what we call a differential form, and those words are being used doesn't really matter much. It's just the idea that this is the notation we'll use because it's important to keep a d something when you're doing an integral. So dx needs to be changed to du. Anyway, let's carefully mark what happens here. The x cubed is your u, and the 3x squared dx is your du. And it's very important that every time you make a substitution that you use both the u and the du equation. If you do not use both, you will not have a proper substitution. Again, make sure that you use both. So when I do that, I get e to the u du. So what happened here? When I made this substitution, I turned it into a much simpler integral. We know how to solve the integral of e to the u. The rule for e to the u is just e to the u plus c. And then the final step is back substitute. U was x cubed. So we get e to the x cubed plus c. This particular example shows one of the common things to look for when you're doing a substitution. The exponent of e or some other base is often a good choice for your u. Let's do another one. For this example, 2x minus 3 is inside the parentheses. Something inside the parentheses, or inside of a root, is often a great choice for your u. Let's try that one. Let's let u equal 2x minus 3. And then remember, du, you calculate. Du is 2 for the derivative, and then we keep that dx as part of the notation. And hey, we're in luck. There's a 2 right here. Let's make our substitution. 2x minus 3 is my u, and the 2 dx makes up my du. What we do is we rewrite the integral using this substitution. I get u to the 4th du. And again, that makes a much easier integral. We know how to solve this one. This is u to the 5th over 5 plus c. And then my final step is simply to back substitute and put u back in. U was 2x minus 3, and then I need a plus c. Simply substitute your u back in for whatever it was before. Next example. Now this one probably looks a little bit strange, so let me tell you, often a good choice for your u, when it's possible, is to let u be the whole denominator. So let's start off with that. Let's let u equal 2x to the 4th plus 1. When we do that, the derivative is 8x cubed, and don't forget your dx. And hey, take a look, 8x cubed is in the problem. Now one thing to note is that if you're going to grab something out of the problem for your du, it needs to be in the numerator when you're talking about a du. The only exception to that rule is sometimes your du might have a 1 over something in its own right. So if it's in the denominator, say here it was a 1 over, then that thing in the denominator you could try to look for as part of your du in the denominator. This part is my u, and again, because it's in the numerator, this part is my du. So what we get here is the u is in the denominator. It needs to stay in the denominator. And du, often I like to write it at the end. So when we get one of these, we just use a placeholder. and call this 1 over u. With that said, we get the natural log of the absolute value of u when we integrate, plus c, and then simply substitute back in the 2x to the 4th plus 1 plus c. Next example. This one is one that I sort of mentioned already. A good choice for your u is the inside of the parentheses, or possibly a root, which is in the same vein of thought. So I'm going to let u equal t cubed plus 5. And that makes du equal to 3t squared dt. But this time, let's go ahead and highlight a few things. Here's my u, but I don't have a 3t squared. Well, what will I do? Here's the secret. What you can do is you can divide both sides of this equation by 3 to get du over 3 equals t squared dt. This particular technique is needed for most of these problems that we'll encounter. Just the first few examples I gave you, I just happened to set it up so that it was easy to spot your du. But keep in mind, for most places from now on, you might need to divide by the constant in front in order to make du. With that said, t squared dt is going to be du over 3 this time. So when we make our substitution, the t squared is gone, it's part of the du over 3. We just get square root of u, and then du over 3. Now, one of the things that I like to do every time I run into a problem like this where you've got an over is bring that constant to the front of the integral. If it's over 3, that's the same as 1/3. And then I've got my du left by itself now. But to integrate the square root of u, I need to do a little bit of a changeover. So let me rewrite the square root of u as u to the 1/2. Now we can integrate this using the power rule. We get 1/3 u to the 3/2 when we do 1/2 plus 1 divided by 3/2 plus c. Let's simplify that a little bit. 1/3 divided by 3/2 is the same as 1/3 times 2/3. We still have a u to the 3/2 plus c. And then we can go ahead and multiply these to get 2/9 and back substitute. U was t cubed plus 5 plus c. So one of the things that we should note is that that technique that I used only works for constants. It is pretty common that you need to do something with dividing by a constant to make the problem work out. But warning, you may only divide constants when you do this. All of your x's or your t's, or whichever variable you're using, must be used up when you make the substitution. So be careful, make sure that your variables match up, because if they don't, that substitution does not work. Let's do another example. X cubed over 1 plus x to the 4th. This is the one where I told you a good choice is often to let the whole denominator be your u. When I do that, my du is 4x cubed dx. And so I will divide both sides by 4 because I don't have a 4x cubed, I just have an x cubed. I get du over 4 equals x cubed dx. So now let's highlight some things. This is my u, and again, the x cubed needs to come from the numerator. So this will become du over 4. Now let's make our substitution. Just like last time, the u is in the denominator, and it will stay in the denominator, which I wrote as 1 over u earlier. And then we get du over 4. Now this will be the last time I do an integral this way, where I go ahead and put the over part. From now on, I'll just go ahead and write the 1/4 in front to make this process a little bit easier. So there's the 1/4 in front, and now we can integrate. This is the natural log of the absolute value of u plus c, which is 1/4 natural log, and if we back substitute, we had 1 plus x to the 4th plus c. So be careful with these constants. Make sure you divide them out if need be, and feel free to write them in the front. It makes the problem easier. Now here's one for you to try. Feel free to pause the video and see if you can get this one, and we'll come back to it in just a moment. Alrighty, let's say u equals t squared plus 1. I'm making this choice because a good choice is the value that's in the exponent when you're looking at the e. So if I do that, I get du equals 2t dt. And again, I need to divide by 2, which I'll just go ahead and write in one step. I get t dt. So by dividing by 2, I'm able to get rid of the extra constant in the problem. Here's my u, and then this part, the t dt, is going to become du over 2. Let's make our substitution. Like I mentioned on the last slide, I'm going to go ahead and bring the 1/2 in front that comes from the du over 2. And then my integral just becomes e to the u du. If you got to this part of the problem, great! Now let's integrate it. The integral of e to the u is e to the u plus c. And then we'll just back substitute the t squared plus 1 back into the problem, and the plus c. These aren't too bad once you get the hang of them. Now let's do a definite integral. When it comes to a substitution, these are a little bit strange. I'll show you two methods, but right now let me show you a method that is a little bit intuitive for what we've done already. What I'm going to do first is simply look at the indefinite integral. I'm finding the antiderivative so I can use the fundamental theorem of calculus. I'm going to let u equal x squared, so du is 2x dx, and that means du over 2 is equal to x dx. This problem is pretty similar to the one that we did on the last slide. Here's my u, here's my du over 2, and then when I make the substitution, I'll bring the 1/2 in front, and I get the integral of e to the u du. Again, the integral of e to the u is just e to the u. And because I'm doing a definite integral, I'm not going to bother with the plus c. I'm just going to go ahead and back substitute and say this is e to the x squared. Now let's jump back into the fundamental theorem of calculus. If I found the antiderivative to be 1/2 e to the x squared, that means I have 1/2 e to the x squared evaluated from 0 to 2. And then let's plug it in. I've got a 1/2 e to the 2 squared minus e to the 0 squared, which is 1/2 e to the 4th minus 1. Off to the side here, I'm going to show you a little method that you can use. Now this is a method that I would not expect you guys to use in this class. This is a method that I would more reserve for a Math 141 class where they're going to be doing more integrals in the future. However, I do want to expose you to it because it's kind of a nice technique. What you could do, if you're starting with the original integral, you've got x e to the x squared dx, and I'm going to use the same u-Substitution. U equals x squared, du equals 2x dx, and du over 2 equals x dx. And then I'm going to make my substitution and still get 1/2 integral of e to the u du. But what about the numbers? It would be incorrect to write 0 and 2 right here, because these values, the 0 and the 2, were values of x. Whereas if you were to write 0 and 2 here, that would actually imply that they were values of u, but they're not. So what we can do is we can actually plug those values into the expression. If I plug 0 in for x here, I get 0 squared equals 0. So when x equals 0, u equals 0. And then how about 2? When x equals 2, u equals 2 squared, which is 4. If I do this, I create a brand new integral, and I will not have to back substitute. I get 1/2 integral of e to the u is e to the u, We'll evaluate that from 0 to 4, which I can immediately finish. Plug in 4, and when I plug in 0, I get 1 from e to the 0. You'll notice I get exactly the same answer. This method is a little bit shorter, but requires a little bit more finesse. So for this class, you're welcome to use either method, but I will continue to use the method up here for our examples, simply because it's a little bit more intuitive to what we've done already. Let's summarize. There's two methods to solve these definite integrals with a substitution. The method that I recommend is always do the indefinite integral separately. Just solve the problem and then go back so that you can plug in the values that you need. The other method is to change the limits of integration so that you get new values for the u-substitution, and when you do this, you will just plug in these new values and you will not back substitute. Like I mentioned on the last slide, the notation's a little bit harder with the first method, but it takes a lot of practice to get used to that second one, and we want to make sure that we can solve these problems. So I'd like to give you guys the way that's the most intuitive. Let's do two final examples with this. For this one, I'm going to let u equal the whole denominator, 3 minus t. If I do that, du is going to be negative 1 dt. And I don't have a negative 1, let's just use negative du equals dt. Now I haven't done one with this little of an amount of stuff in the du, but you'll notice that it should still work the same way. What I get is I have my u here, and then my dt is going to be the negative of du. So if I'm looking at the indefinite integral, this becomes the integral with a negative in front of 1 over u du. Notice I brought the negative to the front of the integral. That gives me the negative natural log of the absolute value of u, which I won't bother with the plus c. I get the negative natural log of the absolute value of 3 minus t. Now let's go back to the original integral. For the original integral, it was 1 over 3 minus t dt. Now I'm going to have the negative natural log of the absolute value of 3 minus t evaluated from 0 to 2. So I get the negative natural log of the absolute value of 3 minus 2 minus the negative natural log absolute value of 3 minus 0. Here I get the natural log of 1. That's just 0, so that goes away. Plus the natural log of 3. So my answer is natural log of 3 for this one. The next example is for you to try. Again, feel free to pause the video and see what you can do with this one. Okay, let's solve the indefinite integral first. So if I do this one, I'm going to let my u be x cubed minus 1, and my du would then be 3x squared dx, so that du over 3 is equal to x squared dx. And then we can get my u on the inside, and the x squared dx is going to become du over 3. If I rewrite this, I'll bring the 1/3 in front, and I'm going to be integrating the square root of u, so let's write that as u to the 1/2 du. This is one we did a little bit earlier. I had a 1/3 u to the 3/2 over 3/2, and again 1/3 divided by 3/2 is the same as multiplying by the reciprocal. I got 2/9 earlier. And when I did that, let's go ahead and back substitute the x cubed minus 1 to the 3/2. Then to finish the problem, we just need to plug in the values. I get 2/9 x cubed minus 1 to the 3/2 evaluated from 1 to 2, which is 2/9, and then I've got the, let's just leave the 2/9 in front, 2 cubed minus 1 to the 3/2 minus 1 cubed minus 1 to the 3/2. We get 2/9 times 7 to the 3/2, And this part is just 0. So this will be my final answer for this one.